You know, when you hit run on a piece of code, there's this incredible, invisible process that happens in a flash. There's a compiler working behind the scenes, and its job isn't just to translate your code, but to make it smarter, faster, and way more efficient. Today, we're going to pull back the curtain on one of its cleverest tricks.
So here's what we're going to cover. First, we'll look at a common problem with how we represent code. Then we'll introduce a much smarter solution called a DAG. We'll see it in action, figure out how it's actually built, and then wrap up with why this all matters so much for performance.
All right, let's get right into it. For a compiler to make code better, it has to understand its structure first. Now, a really common way to do this is with something called a tree, but as you're about to see, trees have they have a big problem.
And that leads us to the big question that every compiler designer has to tackle. How do we map out our code in a way that's not just correct, but is also super efficient and avoids doing any extra work? You see, a syntax tree is a totally logical way to visualize code. You've got your operations and your variables all branching out. But here's the catch. If a piece of your code repeats itself, the tree just repeats itself too. It'll draw the exact same branch over and over again. It's literally doing the same work twice, and it doesn't even know it. Just look at this super simple example. We've got x plus y showing up 2 times. A normal syntax tree would build a whole little structure for the first x plus y, and then it would do the exact same thing all over again for the second one. That is just wasted effort, and in the world of computing, that's a huge waste of time and power.
So, if a tree is so inefficient, what's the better way? Well, it's time to meet the hero of our story, the directed acyclic graph, or as we're going to call it, the DAG.
And right there, that's the secret sauce. A tree has this really strict hierarchy, right? Every little point in the structure, we call them nodes, can only have one parent. But a DAG, it just throws that rule out the window. A single node that stands for a repeated chunk of code can have multiple parents all pointing to it. Basically, a DAG lives by the don't repeat yourself rule. You know, the dry principle that's so important in software development. It asks, why on earth would we build the same thing twice? Let's just build it once and then point to it whenever we need it. It's clean, it's smart, and it's just plain efficient. Okay, theory is one thing, but let's actually see this baby in action. We're going to take a real piece of code and see exactly how a DAG handles it. All right, here's our sample expression. Right off the bat, you can see the repetition, can't you? The variable a shows up twice, and that whole b minus c part is also there twice. A syntax tree would just go crazy repeating itself here. And boom, here is the DAG. Now, at first glance, it might look a lot like a tree, but if you look a little closer, you'll see where the magic happens. Let's zoom in on the important parts. This is where it all clicks. See that node for A at the bottom? Instead of being drawn 2 times, it's just there once, with 2 different arrows, 2 parents pointing right at it. And the exact same thing is happening for the node that represents B minus C. It's calculated 1 time, and both parts of the expression that need it just point to that one result. This is reuse right here. The source material just nails it with this quote. This one single change, letting a node have multiple parents, is what turns a clunky, inefficient tree into this sleek, optimized DAG. It's the whole idea in a nutshell. So how does a compiler pull this off? How does it actually build this thing? Well, it's not magic. It's actually a really clever and surprisingly simple algorithm. Let's walk through it. The entire process really boils down to one simple rule. Every single time, the compiler needs to add a part to the graph, whether it's a variable like a or an operation like subtraction, it stops and asks itself one question. Hey, have I seen this exact thing before? So here's the basic logic. As the compiler scans the expression, it calls functions to make these nodes. But the secret is what happens inside those functions. The first time it sees a, it says, okay, new guy, let's make a new node for you. But the second time, the function checks its memory, finds the a it already made, and just says, nope, no need for a new one, here's a pointer to the old one. It does the exact same thing for b minus c. It's so simple, but so incredibly powerful. So we've covered the what and the how. Now for the most important part, the why. Why do compilers even bother with all this? What's the real-world payoff? And this quote just says it all. There's a double benefit here. It's not just about making the diagram look a little neater. By spotting these common parts, the DAG is basically yelling at the compiler, hey,
You only need to calculate this B minus C thing one time. Don't you dare waste your energy doing it again. And that one little hint saves precious CPU cycles, which means faster programs and apps that feel way more responsive. So let's just sum it all up. Compilers love DAGs for a few key reasons. 1, it makes the internal map of the code way smaller. 2, it automatically finds any repeated calculations so we don't do extra work. And 3, all of this sets the stage for the compiler to generate the final machine code that is just measurably faster. It is a win-win-win. And that kind of leaves us with a final thought to chew on. We've just looked at one tiny, elegant little trick for optimizing a single line of code. It really makes you wonder, doesn't it? What other invisible, genius systems are humming away under the hood, making all the technology we use every single day that much smarter and that much faster than we even realize?